Now that we've been able to describe circular motion in terms of angular quantities of rotational velocity or angular velocity omega and angular acceleration alpha, we can talk about rotational dynamics. Dynamics is indicating a force causing the thing to do its motion. So in this case, forces that cause it to rotate. We've already seen that torque is the applied force that causes an object to rotate. And in order to calculate torque, we know that we multiply the force times the radial arm. So in this case, if we had an object that had a radius r here, and I applied a force F here, perpendicular to the radius, also known as tangent to the path of the circle, then this object out here at the end, mass m, would then rotate along this axis in this direction. We describe the angular motion as omega, and as we're speeding this up, applying the force would also cause an acceleration, an angular acceleration of alpha. So if we take this formula and rearrange to say that the force is the torque divided by the radius, then we can go through and analyze our tangential acceleration. Recall that in our tangential acceleration we were talking about A in our previous video, and so if we look at it in terms of the summation of the forces equal to m times A, the tangential acceleration is the acceleration experienced by this mass along its path, not the centripetal acceleration holding it in the curve, but instead the acceleration that's causing it to gain the angular velocity. So if I take this A and I think about the formula that we had previously, I know that the A here is simply r times my alpha. So I have mr alpha equal to the summation of the forces. The summation of the forces applied to this system causing it to turn in this particular case is just F. So F equal to mr alpha. And then of course we're going to substitute in the fact that F is our rotational torque divided by r, which is equal to m times r times alpha. And then multiplying by r, we yield the result that the torque is equal to mr squared times alpha. Now, what we just did is we took our linear descriptors, which was force and acceleration applied at a rotational radius, and turned it into rotational characteristics, describing it with rotational acceleration at a particular radius and a rotational force. So if we were to relate this to Newton's second law, F equals ma, then this component here, alpha, of course, is the angular acceleration and has similarities to linear acceleration. It describes the change in motion, which here it's not spinning, and then applying F causes it to spin. So this is a change in its spinning characteristics. This portion is very similar to this portion up here, right? But obviously there's an r squared being multiplied. And so what we're seeing is that this characteristic is actually what's inversely related to the accelerated motion. In other words, an object is harder to accelerate the bigger it is. This object is harder to accelerate the bigger it is, or the larger the radius. And so this characteristic is referred to as the inertial characteristic of the motion, right? Whereas this is the inertia of an object in linear descriptions. And so this term, mr squared, is actually a specific term that is defined as moment of inertia. Moment of inertia is a vocabulary word and is given a new symbol, capital I. And so what we've seen here is that I will now be defined as mr squared, right? However, we know that for Newton's second law, it's truly the summation of the forces acting on an object yields its acceleration. And so this particular description was for a single object mass, m, out here at the end. But for an object like a disk or a CD or a tire, there would be multiple masses at various radii throughout the system. And so in that case, the summation of the torques would be equal to the summation of the mass radius squared times the alpha. Now in this case, alpha would be a set constant value, so really it's just the summation of mr squared. So we see that it's really I is the sum of mr squared, right? And so to rewrite this clearer, E is sigma mr squared, summation of the mass and radius squared of all individual masses of the entire uniform object. This is known as the moment of inertia. The moment of inertia is listed like this and is given the units kilograms times meters squared, and is a description of the characteristic inertia factor that is resisting a change in motion when you attempt to rotate it, right? And so we see that the summation of the torques applied to an object causing it to want to rotate is equal to I times alpha. This is Newton's second law as a rotational dynamic as opposed to a linear dynamic. However, the takeaway here is there's a really important factor, and that's the fact that large diameter objects have a greater moment of inertia. So a large diameter cylinder has greater I than one of equal mass but smaller diameter. So that means that for rotational motion, the mass of a body cannot be considered as concentrated at its center of mass. What does that mean? Well, that means that for rotational motion, we actually need to know the shape of an object, because the shape of an object determines its mass distribution, and the mass distribution determines how that object will rotate, right? And so each uniform object has a different distribution of particles, which means that you would have to go through and sum the mass at that particular location for all the locations inside an object. So what I'm talking about is, if I thought about this as a solid circle, then the rotational characteristics of this piece of the circle out here at the end versus this piece here somewhat further in versus this piece here versus this piece here all have different moments, moment of inertias, changing how this system rotates. And then if we think about it in terms of torque, if this was a circle, right, there's a circle around the outside here. When I apply a force this way, the mass on this side is resisting that torque. The mass on this side is resisting in an opposite way around that central axis. And so there is some symmetry that actually cancels out as we include the moments of inertia. And of course, the closer we get to the center, the less moment of inertia there is. So if I have an object that has more mass in the middle and less mass on the outside, it has a lower moment of inertia. That's all to say that I, the moment of inertia, is specific to a body depending on its shape. So on page 208 of your book, you will find that there is a table of various moments of inertia. As we've seen, a mass at the outside of a circle would be mr squared. This is analogous to a hoop, which would be an object where the mass is entirely located on the exterior of the circle. In that case, the moment of inertia is mr squared. However, if I have a cylinder that's a solid cylinder, such as a wood log, or I think of a drumstick rolling down across a snare drum. Since some of the particles are in the center, there's actually an even distribution, and they cancel some out, and so the moment of inertia is actually 1/2 mr squared. Through some other derivations, we find the moment of inertia of a solid sphere, a uniform solid sphere, would be 2/5 mr squared. A stick or a rod, right, rotated like my pen, rotated where I hold it in the middle and spin it this way. Then I have, this is a rod from the middle, would have a moment of inertia equal to 1/12 m times the length squared. If I had a rod and instead I held it at the very end and spun it like spinning a baton or a gun, if I were a rifle twirler in the military, this would be a rod from the end. Then my moment of inertia is 1/3 ml squared. And of course, the last uniform shape I can think of is a basketball, and a basketball is more analogous to a hollow sphere. A hollow sphere obviously is much more closely related to a hoop than it is to a solid sphere, and so we see a much different moment of inertia of 2/3 mr squared. There's a number of others discussed on page 208 in your book, and I advise you to go and read about this further. Each one of these has a derivation that you can do using calculus. In this class we will not, so these formula will be often presented to you, but it will be your job to match up what kind of shape makes the biggest difference. The most common example that I can think of course, is anything in terms of the shapes, hoops, spheres, those kind of shapes make sense. But one very common one is to think about the high bar in gymnastics. If I have someone who is hanging on to the high bar and swinging around and rotating around and going up and around and over the bar, you can imagine that this is very similar, very analogous to a stick being stuck onto the rod and then being rotated around the rod. And so in this particular case, a human, a gymnast, has a different moment of inertia when they're hanging on at the ends than they would if they were anchored so that they have moved such that their hips are closer to the center of the bar, and they are now rotating around at their hip joints, right? And so in that case, it's much more closely related to a bar rotated around the center. And so often we're just trying to match unusual objects with a more uniform shape so that we can describe its moment of inertia. We'll go through a few more examples in class, and I have a demonstration to share with you that should drive home this point.